Assalamu alaikum warahmatullah. Hello guys, today we will continue talking about chapter 5 and today we will talk about supervised learning, unsupervised learning, the motivation for deep learning and what is a manifold and some other concepts. Let's get started. In last videos we talked about logistic regression and linear regression. Today let's talk about supported vector machines and decision tree in terms of supervised learning. So support vector machines are yet powerful machine learning algorithms. They are very good when you have limited computational power, but they struggle when you have huge dataset, and they struggle at generalization. One very good concept technique used in support vector machine is called kernels. And support vector machines belong to the family called kernel machines. Support vector machines works in a way where they try to draw hyperplane in the dataset, and in order to draw the hyperplane they use supportive vectors. Supportive vectors mean supportive data points in order to draw the most optimal line in the dataset which will divide the classes. So generally support vector machine can be used for regression problem and also for classification problem. Kernels used for finding non-linearity in the dataset, and they are sometimes sufficient and computationally efficient. What I can say is that unlike to logistic regression, support vector machines gives they don't give probability of the classification class. Instead they give the actual class as a result. And I think that's all about support vector machines. I said about drawbacks, about benefits, about key features, and let's go to K nearest neighbors and to decision tree. These two algorithms are different and they are special. So K nearest neighbors, they use this voting system, and they don't have any parameters. They depend on the neighbors. So for example, K means number. For example, if we say 5 nearest neighbors, so it means the data point, given new data point, will use nearest 5 other points to find value, to predict. And this is good at some cases it's bad. And if you have imbalanced dataset, it's not good idea to use K nearest neighbors because they tend to not learn properly in that scenario. Decision trees are very powerful. There are many different algorithms, XGBoost and other random forests. They are good. They are like support vector machines. If you have limited computational power, they are good, and they are good for most tasks in machine learning. And decision trees uses concept of tree, nodes and child. Node goes like this, like in tree. For example, if we say if for example let's classify the male and female based on the data, and we will say like if height of person is higher than, for example, 80 kilo, it will go to some place. If it's less, it go to this line, and it goes like this, and it calculates the result, the classification result or regression result. That's about it's shortly about supervised learning. Let's go to unsupervised learning. So unsupervised learning is that it is when the model is given data set which is unlabeled, unannotated, and the model algorithm should find best representation of the data set. So one popular task may be clustering, and another thing is representation. So one application of that representation task is principal component analysis. So principal component analysis is also supervised, belongs to supervised algorithms family, and it helps us to reduce dimensionality of the dataset, maybe from 3D to 2D, and it reduces in such a way that it preserves the information in the dataset. And it is very powerful. It's very powerful, and it uses the concept of eigenvalues and transformation. It's about PCA in short, and now let's talk about K-means clustering. So K-mean clustering means that you give a data set and algorithm should cluster the data set based on the key value. If you put key value like K value as maybe 2 or 3, it will perform based on that key value. But K-mean clustering is also struggles like every other thing. So the authors giving the very good example of trucks and car. Imagine we have cars, we have images. So we have data set of images of red car, red truck, gray truck, and gray cars. And we say to model, okay, cluster these things into two classes. So one clustering algorithm may do in such a way so that it will cluster cars in one case and the trucks in another cluster. But another model, another clustering algorithm may work in different way, so that it will cluster based on the color. It will say red and red cluster, and this one is gray vehicle and red vehicle, and that's not what we want. And actually another clustering method, another clustering algorithm, if we set k equal to 4, it may change into separate cluster, so that it may say that it may say that red car is independent, it's not related to gray car, and it's not related to red truck. But in real world, as you know, red car and gray cars should be closer to each other, and these trucks with different colors, they should be also closer to each other, but these two things should be separated. So the K-mean clusters struggle in that clustering things, and that's all about unsupervised learning in short. And let's talk about stochastic gradient descent. So as you know, as you see so many examples with gradient descent, we use gradient descent and we calculate this cost function or loss function for each data point. Imagine you have million of data samples, imagine, and your computer should calculate cost function for each data point. Is this very efficient? No, it's very insufficient, very expensive. So what stochastic gradient descent does is that it takes from these millions of data samples some sort of them, some small group of them, and it performs the gradient descent cost calculation based on this small function. So from this million of data set, we will take only, like maybe this row, this row, this row, and we will have small data set. And we will calculate on this small data set the cost function calculation, and which will replace this calculation. So they are saying that we can learn, we can learn, we can give the machine learning model, or like the system to learn based on the performance measurement on this small data set from this one. And it might be constant also if it is m size. So that's about stochastic gradient descent. Then in book they are saying that we can divide almost all machine learning models into 4 components: data set, it should have data set, and optimization procedure, the model itself, and the cost function. If we can interpret all machine learning models into these components. And now, final topic: challenges which motivated deep learning. One of the big challenges is that yet these machine learning models cannot solve AI tasks like face recognition, or like speech recognition, object detection, and etc., which are very straightforward for us, intuitive for us to learn, but yet they cannot achieve that. And there is one concept of curse of dimensionality, which says that many machine learning problems becomes exceedingly difficult when number of dimensionality in the data is high. So they are saying that as the data dimensionality grows but data size doesn't grow, it makes machine learning models to perform very poor. I have some screenshot, some graphs. So here we can see that in here it is 1D dimensionality, here 2D dimensionality, there is 3D dimensionality, and yet for machine learning it becomes very challenging to solve or to live in this dimensionality, because they expect to have higher data samples compared to the data dimensionality. That's simple what I understood from this curse of dimensionality. Then there is another concept. It's talking about smoothness regularization. So here, what very important I think is that let me to read one thing. Among the most widely used of these implicit priors is a smoothness prior, or local constancy prior. This prior states that the function we learn should not change very much within a small region. So it's saying that there is a concept of smoothness prior, which says that the function we learn should not change too much in the small region. So that it means that neighbor, it means that if we give some value which is close to previous value, the resulting value should be closer to the predicted value. Make sense? Imagine, how can I say? For example, this is one prediction, and we give some kind of value. We give x, and we receive this prediction, this coordinate. And if we give x plus 1, we should receive some kind of value near to this value. This is traditional machine learning idea, concept. And according to the book, they are saying that this is limitation. This is not what we want. And next thing I want to talk is manifold learning. So manifold is a connected region. Mathematically, it is a set of points associated with a neighborhood around each point, From any given point, the manifold locally appears to be a Euclidean space. In everyday life, we experience the surface of world as 2D plane, but it is in fact a spherical manifold in 3D space. So it's saying that we can not represent our world as 3D, but instead we can put it into 2D plane. There is one example. When the data lies on low-dimensional manifold, it can be most naturally for machine learning algorithm to represent the data in terms of coordinates on the manifold, rather than terms of coordinate in real world. In everyday life, we can think of a road as a 1D manifold embedded in 3D spaces. We give direction to specific addresses in terms of address numbers along these 1D roads, not in terms of coordinates in 3D space. So we are saying that we can somehow represent these real higher dimensional spaces into the efficient and small manifolds, which are much more efficient at doing tasks. And sometimes according to the book, they are saying that finding the manifold coordinates is challenging, but it's saying that it is promising for improvement of many machine learning algorithms. So this short introduction to manifold, and it is uniformly sampled images, so which means it's just no random noise, and this data set is manifold of the human face. So it's saying that it is two-dimensional manifold corresponding to the two angle of rotation. So this is kind of example of manifold, and with this one, it is end of our chapter 5, and we are coming to chapter 6, and that's it for today, guys. Please read chapter 5 by yourself. Check the deeplearningbook.com. It is not too much boring, but yet very informative. And if you have questions, ask in comments. If you want to see the practical implementation of the classical machine learning algorithms, check my videos. Maybe some of them are implemented already. And see you all in next videos. Bye bye.